Okay, so here's another example of the application of tau equals I alpha. Okay, but here a few more things are happening, so let's make sure we understand this problem correctly. So the question is asking is if you are, there's a pulley again, and we have a string wrapped around it, and we have a mass m attached, and this mass is going to fall, and as it falls, what is the acceleration of the mass, and what is the angular acceleration of the pulley? Okay, so let's do this. So the first thing we'll do in these cases, all right, is draw free body diagrams for the object. So for the hanging mass, the free body diagram is very simple. It is going to be the weight of the object. It's m. The weight of the object pulling it down, mg, and then you have the tension pulling it up. Okay. Now, just for the to allow us to calculate things better, we know that there is an acceleration part, so MA part, that points down as a result of these two forces, which is essentially just writing Newton's second law. Okay. On the other hand, for the disk, we have some force that is pulling it down. Now, the most common mistake that people make is that they say that this force is equal to mg. Okay, but it is not. Okay, so this force is not equal to mg. If you think about it, the only reason the pulley is turning is because of the string. So it is the force that the string exerts on it is what causes it to turn. That force is equal to T, right? So please be very careful with this. And once we know this, we can calculate the torque due to this force and then do all the stuff. All right, so let's write our equations now. For the hanging mass, my equation is mg minus t equals ma, and then for the pulley, we know that the torque, which is r times t times sine of 90, which is 1, is equal to I times alpha. So now we have two equations, but we have three unknowns. We have t, a, and alpha. Now, we're going to assume that the string is not slipping on the pulley, and if that's the case, then we also know that A is equal to R alpha. Okay, so what we'll do is in the second equation, we can replace alpha with A over R. Okay, so I can rewrite R times T is equal to I A over R, and then we'll do another thing. We'll divide both sides by R. Okay, and this ends up giving us T is equal to I over R square times A. So I'm going to write the other equation down once again, which is mg minus T equal to ma. And it's always useful to write T in this form because you see that I can simply add up these two equations now and eliminate T. So this gives me mg is equal to I over R square times A plus m times A, which is equal to I divided by R square plus m times A, and this ends up giving me A, which is equal to mg over I over R square plus m. And once I know A, we can find alpha. Alpha is simply A divided by R, so this ends up being equal to mg over R times I over R square plus m. Now some of you may want to simplify the first term actually and rewrite this as mg times R square over I plus m R square. And the way I do this is by dividing the numerator and the denominator by R square, which basically eliminates the R square in the denominator, and then I have to multiply, I have to distribute it, and so I get an mr square term. And then on a similar basis on this side I could also get mgr over I plus mr square. So these are all equivalent things. Now once I know alpha or A, we are also able to find the tension in the string, which is simply equal to I times A over R square. So that, if we do it, I simply get I times A, which is mg R square over I plus m R square, but I divide by R square, so we are simply left with mg times I over I plus m R square. Okay, so simple problem. Once again, just remind yourself, break everything draw your free body diagrams, just remember that it is the tension, okay, that is responsible for the torque and not mg entirely. Only, if you see, tension ends up being less than mg, so we need to understand that. And then the rest of it is basically just doing some simple algebra.